Hey, what's going on? Um, I know how to explain the double slit experiment. So, just briefly to describe it, the double slit experiment is where you shine a laser at two slits, very small slits, and there's a board detector on the other side of the slits that determines where the photon lands. And when you shine a laser, either full of light or a photon at a time, it will generate a probability wave. That is to say, there's a certain probability for where the photon will land on the other side of the slits. This is pretty normal behavior, as you would probably expect of a photon and of an electromagnetic wave. Um, there's a certain probability that a photon will land in the middle or on the sides. It gets weaker on the sides, which is pretty normal. The weird part comes in when you add a detector, and from the way that I've learned that the detectors work is on the other side of the slits, a detector will interact with a photon that passes through one of the slits. I'm going to use this particular model. And the detector interacts with the photons that pass through one of the slits. The reason, or okay, hold on. So what happens when this happen? When you do this, is the probability wave collapses, as they say, into just two slits, two lines. There's so instead of having a bunch of lines across the detector screen, you just get two, which mimics the two slits. The reason why this happens is because when a photon passes through a slit and then is then detected, which is otherwise, in other words, it is interacted with, the time it takes for that photon to reach the detector board is different than the time it took the uh, unimpeded photon that it took to reach the detector board. So what's happening really is that the photon passing through the slit undetected is passing through the slit normally. And the photon that is passing through the slit, which is being detected by a detector that is interacting with the photon, is causing the photon to reach the board at a slightly different time, a later time. And I think you could prove this if you measure the redshift for the photon that passes through the slit that was detected. If you measure the redshift, the amount of redshift compared to the color of light that the photon undetected is measured as, I think this would prove my point perfectly. And that so and so when this happens, when one photon is passing through the slit at a different rate of velocity or speed than the other slit, it disrupts the entire wave probability. Because originally, you have a wave probability for each path of light possible. Because even though it is one photon, there is still a cone for the probabilist. How do I say this? There's still a cone, a narrow cone, but a cone nonetheless for where the photon can go in the range that it is shot at. A good example. I'll show you an example. real quick, kind of. If I can find, where's my laser light? I have a laser somewhere. I don't know where my laser's at. Oh, there it is. So what I mean by this is you could see this is like the middle probability of the wave right here. And then all around, you could still see the laser. You could see where the laser is being shot at, but the probability for a single photon to land, for example, in this direction, is lower than it is for this direction. So that's what I mean by a cone of probability for it to pass through the slits. And then once it goes through the slits, the wave interacts with itself. And it can do this because all of the probabilities align at the same time when it passes through the slit. So, like this right here, all of the probabilities are aligning at the same time. So, if I had two slits between me and my camera right now, all of the paths that the light is taking is happening at the same time. But if I suddenly had a detector between the camera and the slits that this would be passing through, the time it took for the detected photon to reach the camera would be at a slightly later time than the photon that was undetected. And so this causes a collapse in the wave probability. And instead you get a photon undetected and a photon detected. And that's it. And you could prove this if you are able to measure the redshift of each photon. It's probably the best way to do that. I can't do it, but if scientists could do it, they measure the redshift of each photon. Boom, bada bing, boom, boom, bada bing, bada boom. And if they did this, and for some reason I was wrong, it would be even more mysterious because then you would know that even though a photon is being detected, interacted with, and landing on the detector screen, it's all happening at the same exact time. If I was wrong, but I don't think I'm wrong. I don't think I'm wrong. I could be, but I don't think I am. I think the photon being interacted with is landing on the screen at a later time, disturbing the probability wave. Something along those lines, anyways. Anyway, see you.